Chapter 4 is going to get us focused in on reactions that happen in aqueous mediums. So we'll start by talking about a little bit about aqueous solutions and what they are. We'll get into the specifics of precipitation reactions and acid-base reactions. And then we'll follow that up with the other topics in this chapter. So we should recall that dissolving involves the breaking apart of the solute particles by the solvent particles. So on the left, we can see that we have water molecules surrounding the ions in an ionic substance, breaking it apart. So you see how that ionic lattice, that crystal structure, is being pulled apart by the water molecules, where the hydrogen end of the water molecule is surrounding the negative ions, or closest to negative ions, and the water molecules surrounding the positive ions have the oxygen end pointed toward the positive. On the right, we have methanol, and methanol also is a liquid, so when it dissolves in water, it will just mix in with the water as a solvent. But you notice that in this case, the methanol does not break apart at all. It stays together in as its formula unit, or as its molecule. One of the terms that we use to describe solutions are whether the solutions are electrolytes or non-electrolytes. So the video here will show you what that, what's referred to as an electrolyte and a non-electrolyte.
Hydrogen chloride is a colorless gas which is soluble in water and benzene. First, pure water is poured into a beaker. Water has a very low conductivity, and the bulb remains unlit. When hydrogen chloride gas passes into the water, it dissolves, and the bulb shines very brightly, showing that the solution is conducting. Ions form because water behaves as a base, accepting protons from the hydrogen chloride. We get the hydronium ion and the chloride ion. In the last part of the experiment, we are using a weak acid, acetic acid. We pour 0.1 molar acetic acid into the beaker, and the light bulb glows less brightly, showing that the solution has only a small conductivity. Acetic acid is a weak acid and is only slightly ionized in water.
So let's take a look at what's happening on the molecular level here. So in the first case, we have our non-electrolyte, and here you'll notice that there are no charged particles. Now they've left the water off out of the picture here, but there are no charged particles there, making it impossible for electric current to flow through. Over on the far right, we have a strong electrolyte. So this was the second example where they had hydrogen chloride gas bubbled through water, in which every single hydrogen chloride molecule broke apart into a positive and negative ion. Thus, it was able to conduct a significant amount of current. In the last example, that was a weak electrolyte. They had acetic acid. Acetic acid, when you put this into water, some of the molecules break apart, and thus some current can form, but most of the molecules actually end up staying together. So these terms, electrolytes, non-electrolytes, weak electrolytes, and strong electrolytes, are terms that we need to be somewhat familiar with. So just to kind of bring some of these out again, we've got aqueous solutions, solvent, solute, solvation, the process of dissolving, non-electrolytes, weak electrolytes, strong electrolytes, and equilibrium, which is the balance between what is dissolving and what is not dissolving, what is breaking apart and what's not breaking apart. And we'll talk more about equilibrium at a later date. Precipitation or double replacement reactions. So you can see in the picture, our macroscopic view, we have two clear colorless solutions on the left. When we start to pour those together, we get a yellow substance forming. That yellow substance actually is a solid. You can tell by it being so cloudy, and after a while the solids settle into the bottom in the picture on the right. If we look at our theoretical model for what we think is going on here, we have in the solution that's being poured potassium ions and iodide ions. In the solution in the beaker that's on the bottom, we have nitrate ions and we have lead ions. The reaction that occurs here is between the lead and the iodide. So you can see at the bottom here, the lead and the iodide have come together and formed clumps of solid. Absolutely nothing has happened to the nitrate and the potassium. Those two ions basically have just been watching the lead and the iodide come together to form the yellow solid that's in the picture above. If we write the equation for this reaction, we would have potassium ions plus iodide ions reacting with lead ions plus nitrate ions forming lead iodide solid. And again, as I mentioned before, the potassium ion remains unchanged, as does the nitrate ion. Okay, and then we want to balance the equation. Balancing both charge and number of atoms on each side. So this would be known as the total ionic equation. Quite often we shorten this down to just the net ionic equation. In the net ionic equation, we're going to leave out the spectator ions, the ions that do not react. So that would be our potassium and our nitrate. Those two ions remained unchanged, so we would rewrite it with our iodide ion plus our lead 2 ion, producing lead 2 iodide. As the solid precipitate. To determine which solids are formed in a double replacement reaction, you need to know the solubility rules. The table in front of you here is also found in your text on page 127. You basically need to know all of these rules. The fact that all nitrates are soluble is very, very important. That will help you identify what is the precipitate in most cases. The rest of the rules, there's some exceptions to them, but most of the time, they go with the common theme. For instance, chlorides, almost always soluble except for silver, mercury, and lead, mercury 1 and lead. So just make sure that you have kind of put this table to memory.